talking about Chapter 17. Chapter 17 is energy and momentum methods for rigid bodies. And as you can see, the PowerPoint slides are 1 through 26, but there's not that much lecture material. The first several slides are about the lecture, and then there are 5 example problems worked on the PowerPoints. So we'll spend most of our time just talking about the principles, and then I'll put up a couple of example problems for you so that you'll have them in your notes. But it's the material here, there's a lot of stuff that we're building on from previous discussions that we've had about energy and momentum methods. And today specifically, we're going to talk about the conservation of energy and the work energy principle, which we've talked about for particles, and we're just going to extrapolate that a little bit into a discussion involving rigid bodies. So taking a look at our PowerPoint slides, the first thing is that the principle of work energy, that the kinetic energy at state 1 of a system plus the work done from state 1 to state 2 is equal to the kinetic energy of a system at time 2, is really like the basis for solving these ideas about the displacement of velocity. The principle of impulse and momentum, which is covered in the second part, we're going to talk about that in section 17.2. So today we're going to limit our discussion to the work energy principle, and then we'll also view it in this form and then also as potential energy at state 1 and state 2 being the conservation of energy principle. So if you remember sort of the difference in math between work energy principle and other things that we've done in this class is that work and energy are quantities or scalars. They are not vectors. So when we start talking about work and energy, we do have to think about the directional properties associated with work in that it's a dot product, but we don't have that highly vectorized math that we do when we start talking about momentum. And so when we talk about when we start talking about work done from state 1 to state 2, and we have that dot product of F dot dr, that the magnitude of that is going to be F times the cosine of the angle between the direction of motion and the force. So what we're really discussing there is the fact that work only occurs if it produces movement, and the amount of movement is proportional to the amount of work. So if, for example, I push straight down on a horizontal table and the table doesn't move, I've expended quite a bit of force, but I've not really done any work. In other words, the work requires a movement, and that's really what that cosine of alpha is. So the closer the direction of the force is to the direction of the movement, or even if it's constrained like a table that's not going to fall through the floor unless I break something, the closer the direction of the force is to the direction of the motion, the more work you get from the same amount of force. It's basically what we're talking about. And so this discussion is really pretty similar to our discussion of points or particles. Now, when we have a rigid body, we also have to start thinking about if the body is going to rotate or how it moves with respect to the rest of the body. So we can't just consider it to be a point in space. And at this point, we also have to think about that force creating a moment and the moment moving it through some angle. So the dimensions of the work caused by a moment, this is actually the moment of a couple, because, right, you're not going to be able to pull it outside of the integral if it's not a constant. But if you have a moment of a couple and it turns a body through some angle theta, that the work done from state 1 to state 2 in that turning is equal to the moment of the couple in this case, times the change in the angle. And if you look at the dimensions on this, work is in units of foot-pounds or Newton meters. A moment is also in units of foot-pounds or unit meters. So we need that theta to be dimensionless, meaning that we need to work with it in radians. So if you work with it in degrees, you have to convert it to radians in order to keep your dimensions or units consistent. Right. Now, the other thing is that if you don't move things, you're not going to do any work. And this just breaks it down. So if you have a pin or a connector of some sort, and you're not moving through that pin or connector, there's no work being done, even if there's a force applied to it. And that's that sort of trivial example I just gave you of me pushing down vertically on a horizontal table. Unless the table breaks through the ground, it's not going to go anywhere. I'm not going to be doing any work. Also, forces acting in a direction that's perpendicular to the displacement at that point. So if there were more forces, if somebody was pushing this table in that direction, but I'm pushing down on it, their force is doing work and my force is not. Okay, so it's that same idea over and over again. Although sometimes it's just harder to ferret out. It's harder to tease that out of a problem of a rigid body than it is to really remember that that's the way it works in real life. And then also friction forces at a point of contact that are rolling without sliding don't do any work either. All right, so if we go back to the idea then and look at kinetic energy, we can say that if we have essentially the kinetic energy of the center of gravity, that's 1/2 mv bar squared, where v bar is the velocity of the center of gravity, and then we consider the angular velocity or the rotational properties about that center and add in 1/2 I bar omega squared, we're going to have an expression for the kinetic energy of the rigid body at a particular time. So when we talk about a particle, we don't have to think about this second term because everything's all about translation. Particle can't rotate. So when we have a body that can rotate, we have to take into account the rotational piece of that as well. And once again, if you work this out, that would be a mass moment of inertia. You'll see once again that the units are consistent, or units of energy. All right, so the kinetic energy of a rigid body then is separated into those two things. The kinetic energy associated with the motion of the mass energy, and the kinetic energy associated with the rotation about the center. And if it's rotating about a fixed axis, that means that there's really, everything is all about rotation, and it just turns out to be the half times the I omega squared term if we have a pin stuck in it and it's just rotating about that same axis, which can greatly simplify a lot of problems, by the way. I mean, you can start at the beginning and work that out every single time, and you'll see that everything pops out, but it's just something that if you know that going in, you can simplify your work. All right, so then for problems that involve systems consisting of several rigid bodies, which are just several rigid bodies can just be thought of as a summation of points. And so instead of being an integral, you're going to have a summation sign, but it still works kind of the same way. So still the work energy principle is 100% true. In the light of, well, non-conservative forces, but that's still as true as it was before, let's put it that way. So it's no less true than it was when we started talking about this. So T1 and T2 are the arithmetic sum of all of the kinetic energies. So we're going to maybe have a summation sign instead of an integral sign. And U from 1 to 2 is the work of all the forces acting on the various bodies, whether those forces are internal or external. So if you have two bodies that are comprise a system, then you have to think about both the external forces to the system and the internal forces within the body. So then again, we can eliminate some of this stuff where we have connectors, where we have pins, blocks and pulleys connected by cords that don't stretch, and mesh gears. The internal forces occur in pairs of equal and opposite and are therefore produce no work. Points of application of each pairs move through equal distances, and the net work of those internal forces is 0, and work on a system reduces to the work of the external forces. Now that is a greatly simplifying assumption on a lot of different, it's not even an assumption, it's a greatly simplifying fact. So like if you have two gears, they mesh together, you have a force acting this way on one gear, a force acting the other way. If the teeth aren't going to break or the gears aren't going to slip, those forces have to be equal and opposite. And in that case, you're not going to get any work. So you can look at the gears without thinking about the force with which they mesh. So those could be very much simplifying assumptions. All right. So when we talk about the conservation of energy, this is where we just look at those potential energy terms rather than looking at the work done from 1 to 2. And, sometimes it's a little bit hard to separate those two out because dimensionally they're equivalent, T and V, but especially the difference between V2 and V1 and the work done between 1 and 2, sometimes the lines of those are just really blurry. But if we separate it out into potential and kinetic energy, the reason we would do that is because we have those fixed points of kinetic and potential energy. So like if you look at this particular bar, we have a sliding bar and we have some sort of a slider here and a slider here. Well, if we consider this our datum, the motion is very constrained, but B is going to slide down, and that's going to cause A to slide to the left. So if we look at it that way, one really neat thing about it is that if it's at the beginning, if we consider the datum to be at the same level as A and B at the beginning, that both T1 and V1 at the beginning are equal to 0. That means that all the energy is going to be turned into kinetic energy, which is always positive, and a negative potential energy, which of course is shown right here. If B drops in elevation, its potential energy decreases. So the potential energy of A stays the same, but we have a kinetic energy of A when it's moving at time 2 and a kinetic energy of B as it moves at time 2. So when we set that up, we can say 0 is equal to the kinetic energy at T2 and the potential energy at T2, and we can solve for this omega based on that idea. So this is kind of an important, there's a couple of equations that I really want to point out. When you have something like this, thinking about kinetic energy as having those two components, a translational component of the center and then a rotational component, greatly simplifies it, because then you can take this original equation and just use it, just realizing that there are two terms instead of one. All right, and so then the last idea that we talk about in section 7.1 is the idea of power. And I think by now that we've talked about this enough, is that the difference between power and energy is that one is an amount and one is a rate. But the derivation of power as being the rate of change of work with respect to time will also yield, if the power is being caused by a force acting on a body with a particular velocity, it's also F dot V. That, philosophically, if you think about like a car engine, there's a certain kind of power that's associated with speed and a certain kind of power that's associated with torque. And dimensionally they're the same, but they're not really functionally the same. So when we're talking about this type of power, we're talking about the kind of power that is associated with a velocity. So it's kind of a fine point. It's not going to come up in this class, but it's something, because I've had students in the past ask me about that, and it's like, yeah, they're not exactly the same. Like, we're talking about the drawbar horsepower on a tractor or a horsepower of a very fast race car. They're dimensionally equivalent. They have to come from the same place. It's a conversion of mechanical energy, but functionally they're a little bit different from each other. All right, and so then if you continue that topic, we know that that du is also equal to m d theta when we have that rotational piece, so that power is force times velocity. It's also a moment, as in the moment of a couple, times omega, or that rotational velocity expressed in radians per second. All right, so if we have something like this, I think I'll just probably do 2 sample problems with you today, or go through the ideas with you. Flywheels are amazingly simple and yet effective mechanical applications. And flywheels tend to just be extremely heavy in mass and have the rotational properties are sort of the biggest deal. And what they do is they store a lot of energy because they have a very high moment of inertia. So they're hard to get rotating and they're hard to stop rotating, which is sort of the point of having a flywheel in the first place. So here we have a drum with a flywheel, and we're given the centroidal moment of inertia. We have bearing friction that is equivalent to a couple of 60 foot-pounds, and at the instant shown, the block is moving downward. So we have a velocity, we have a radius, we have a moment of a couple, and we're given the mass moment of inertia of the centroidal the centroidal mass moment of inertia for the drum and the flywheel. So they ask us to determine the velocity after it's moved 4 feet downward. All right, so we're covering a distance of 4 feet. We have a force times a distance, or a force times velocity, if we were talking about power. And if you look at the configuration, you can see that the velocity of the center, which is at A, is going to be equal to r omega. Okay? And that r is going to be the r of the drum in the middle, of course, because we're talking about this cord. The velocity of the weight is going to be the same as the velocity of the cord. All right. So if we consider the system of the flywheel and the block, we can say that the work done by the internal forces are exerted on the external cable, and the velocity of the block and the angular velocity of the drum are related by this relationship, because we're talking about this cord. The word that they use is inextensible, just meaning that it doesn't stretch, which means that whatever velocity is coming off right here is going to be the exact same as the velocity of the block. So we were given the velocity of the block, so we can backtrack and find the rest of the stuff. We can find out what our omega is of the entire apparatus, because that's just V is equal to r omega. So we can get our rotational velocity. All right, and then we know that the rotational velocity of the drum and the rotational velocity of the flywheel are going to be exactly the same. So we can apply the expressions. We can start thinking about the potential, or the work energy equation by considering what is the kinetic energy of the system. So we know that it's 1/2 mv squared plus 1/2 I bar omega squared. We add those two terms together and we come up with a value for the kinetic energy at time 1. The kinetic energy at time 2 is going to be equal to whatever we've dropped through for those 4 feet, and then the difference between them would be the work done. Okay. Of course, we have to take into account the moment of the couple as well, because we're bleeding off energy that way. But the entire work is going to be the difference, and then we have to subtract out the opposing frictional work done as well. All right, so we add that together, and we can come up with the velocity of the center at time 2. So as you can see, there's a lot of parallels. They're longer problems. There's more involved in it, but there's a lot of, you can draw on the work that you did with particles. You just have to think about the kinetic stuff, or the rotational stuff as well. All right. The next one is a gear problem. I'm not going to go through the whole thing, but once again, when you mesh those gears, forces are equal and opposite. So you're not going to have any work associated with the forces of the gears meshing if you view it as a system. All right. Problem 3, we have a sphere, cylinder and hoop, each of which have the same mass and radius, and were released. We want to determine the velocity of each body. I'm not really crazy about this problem, but it's the same ideas. Sorry, I'll find there's a more interesting one. 7.5 or 7.4 are a little bit more interesting, but yeah, they're all the same. So what we're going to really be comparing is what the rotational properties of those 3 shapes are. When we come up with 17.4, we have a 30-pound slender rod, pivots at point O, so we have a fixed connector there. So we know something about that point. It's not really going to be moving. There will be forces acting on it. Forces are not going to be producing any work. Okay. We have a spring. We know what spring energy looks like. It's 1/2 kx squared, and it's compressed 1 inch, and the rod is released. Determine the angular velocity and the reaction at the pivot as the rod passes through a vertical position. Okay, so it's going to come clear up here, swing vertically. All right, so we still know, go back to the basics, the energy at time 1, kinetic plus potential, is going to equal the energy at time 2, kinetic plus potential. So we can take a look at what goes into the kinetic or to the potential energy. We have a gravitational and we have a positional. And we have the spring energy and the fact that when we move it upward, there's going to be an energy of position associated with that. Okay, so we have a V1 and a V2. And then we can talk about our T's. Once again, we have mv squared. We also have the I bar omega squared term for situation 2. And when we get to the vertical position, we could probably make some assumptions about the velocity center. Not really. We can't really do that. In other words, we can't really assume that it's going to be 0 because it could be coming back through. It's not like a projectile. There's no reason to expect that it's going to reach a 0 velocity at that point. The only thing we can really assume is that it's not even really assumption, but right here, if we consider this the datum, that the potential energy due to elevation at time 1 is going to be 0, and we can geometrically determine what it's going to be at position 2. All right, so from that analysis then, where we take our kinetic energy and potential energy at time 1, equate it to our potential plus kinetic energy at time 2, we can determine omega. In other words, how fast it's spinning right there. And then we can use a little bit of the discussion that we had in the last section about moments and effective moments, forces and effective moments, effective forces in order to determine the reactions at the pin. Because once again, you're not going to be able to get those reactions at the pin out of thinking about the work energy principle or kinetic and potential energy, because there's an internal force at a fixed location. They're not going to pop up into those equations. All right, and the last problem, whoops, there we go. The last, not the last problem of the whole thing, but the last problem of this set. We have these two slender rods. We have a constrained motion. A is pinned. D is constrained to be purely horizontal. So we can, once again, if we wanted, we know the mass of the rods, and the system is released when beta is equal to 60 degrees, and we want to determine the angular velocity of this rod, AB, when beta is equal to 20 degrees. So as that folds down and goes from a high of 60 degrees down to a low of 20 degrees, and it will be rotating through there. It's not going to stop or anything. And what the velocity of point D is at that exact same instant. Well, the interesting thing about D here is when you do your analysis, of course, that D is going to be constrained. All right, so we can start by saying energy is conserved, kinetic plus potential at time 1. We can say what we know about those things. Okay. And so since we have the pretty good geometry, we can say quite a bit about the potential and initial conditions of the initial and final of the potential energy. And then this gets a little bit more complicated just because of the geometry, because of the trig. But basically, and I wouldn't put anything that's hard on an exam, I want to make it really clear. But basically what we're still saying is that we're getting those components of the velocities at those particular times, and we're equating them to a translation and a rotation. So A is just rotating, and D is possibly doing both, but it's purely, the sum of those things is going to be purely horizontal. Okay? And so then once you get your geometry worked out, you can come up with an omega, and then you can come up with a VD. This problem strikes me that you could do this more easily using Chapter 16 methods. So I don't think you really, I mean, because when you have something that's that clear as a vector, you've already kind of won half of the battle. So I think that finding the velocity of d would actually be easier. I don't even think I would need chapter 16. I think I could just do it with the geometry. So I think you guys could too. Anyway, but there's some sample problems. So I think that 1 and 2 are interesting problems. 4 is relatively interesting. 3 and 5 are not as interesting. So, or is not as applicable. So, but that gives you a couple of things in your notes to take a look at. So do you guys have any questions at this point? My advice to you when you're working on problems on chapter 17 is to build on the information that you already know about the motion of particles, doing energy analysis of particles, and then just thinking about T being split into the translational and the rotational part. And then I will try to select problems that are well suited to this. Like I said, I don't really think this problem is very well suited to that analysis. So I'll choose problems for your homework that are well suited to the analysis of energy methods. All right? All right, and I'll give you 2 homework problems. That's it for today, gentlemen. So we'll have 2 homework problems put up, and then we'll do section 17.2 next time. So have a good day.